continue lecture. So we are talking about, so this is part 3. Okay, and we discussed about the activity, yeah? So in the last class, we were talking about activity. So activity of I was defined as activity of partial pressure of the I in the above actually the pure solid or liquid pressure compared to the partial pressure of I which is developed over the actually the your solution phase. That was definition. Okay, this one was expressed by activity coefficient and the mole fraction, and we call this one coefficient. And activity coefficient is function of the composition and the temperature. Okay? And there's the two kinds of the limited case. So one was when xi become almost 0. So we call this one as Hennian solution region for the I. And when in this case, activity of I is activity coefficient, but constant activity coefficient times mole fraction. And this is, we call it coefficient. This is only function of temperature, not depending on the composition. Hennian activity coefficient. And we'll say this one as Henry's law. Okay, the other extreme case, when xi now become almost 1, and we call this one Laurentian solution. And in this case, activity I equal to activity coefficient. And this is almost 1. And we call this one Raoult's law. Okay, this is what we have learned last actual class. And why we actually then learning the activity is because from the activity, we want to now express the Gibbs energy of the species in the solution. So Gibbs energy, Gi, molar Gibbs energy of I in the solution is Gi naught plus RT ln activity of I. And compared to this one as a liquid phase, or gas phase was, so this was for the gas phase, and this was for the solid or liquid solution. Here, this one was so-called partial. So in this case, molar Gibbs energy of I species in solid or liquid solution. And this is, of course, standard Gibbs energy of I species, either solid or liquid state. And then this one is basically activity. So in thermodynamics, I believe this is very, very, very important equation. If you want to understand the solution thermodynamics, this is the only one you have to really remember. The rest of them is all solved from here. Okay? So, now let's look at the so-called ideal solution, regular solution, and some general solution for the solid and liquid state. So this one was, activity was the number 1 and probably it's 2. Sorry. Gibbs energy. Gibbs energy of solid or liquid solution. So whenever now you have Gibbs energy of solution, so this is basically molar Gibbs energy of solid or liquid solution. Okay? This is sum of mole fraction of that species times partial Gibbs energy of that species in the solution. For all the I. This is always working for both. This is for both solid, liquid, and even gas solution. This is always true. So whenever you have solution Gibbs energy is sum of partial Gibbs energy times mole fraction. Okay? So when it was gas phase, the gas solution was mole fraction of I times partial pressure of the Gibbs energy of partial Gibbs energy of I in the gas phase, and partial Gibbs energy containing the partial, actually the partial pressure term, and in the end you can actually express, and the partial energy term is just function of the mole fraction times total energy, total pressure. If total pressure is 1 atm, you can actually express this one as a kind of the ideal solution, ideal gas solution. Okay. But now actually, if you express this one for the solid and liquid phase, because that activity coefficient term maybe not equal to 1, so you can have slightly different actually the expression. Okay? So when you have this is solid or liquid solution for the binary system, so GA XA plus GB XB. So let's take this one as a binary or liquid solution. Then we have AB in the system, and GA is the partial Gibbs energy of A in the system, in the solution. GB is the partial Gibbs energy of B in the solution, and the mole fraction of each in the solution is XA and XB. So this is expressed in this way. And then GA, if you actually look at that expression as a function of the activity, then this is GA naught plus RT ln activity of A, and the mole fraction of A plus GB naught plus RT ln activity of B and mole fraction of B. Okay. Now, okay, activity is activity coefficient times mole fraction, as I mentioned, yeah? Activity coefficient times mole fraction. So this is activity coefficient and time mole fraction. So we can actually separate this one as a two ln term, yeah? So if you do that, we can get in this way. XA, so GA naught, so this first term, so this one came out, plus this one coming out from here, because this is mole fraction, this one and XI. So XA and the activity coefficient times the mole fraction. So same thing for the other one. So then we just take the mole fraction term first, and then in the second part, so this way. If you look at this one, so this is just summation of the two Gibbs energy for the pure, actually, the species. Okay, linear change of the Gibbs energy from the pure A to the pure B. Okay, and this one is the ideal mixing term, ideal mixing entropy term. Yeah, do you understand this one? Because in the ideal gas solution, we get exactly the same expression, ideal gas. And we call that this one, so this is Gibbs energy equal to RT, this term is R, so T times minus T times minus R of this term, and we call that minus R XA ln XA ln X plus XB ln XB, that's the ideal entropy term. So ideal mixing term. Is okay? So that's exactly the same term here. So this is basically, so minus T delta S over the mixing, ideal. That's this term. And this is so-called mechanical mixing term. So I mean, mechanical mixing means there's no chemical interaction. So you have the pure A, pure B, linear interpolation from the pure A to the pure B, mechanically. There's no chemical solution, it's mechanical. Just summation as a pure to pure. Okay, so this is linear from pure A to the pure B, and this is minus T ideal entropy term. And then this one is now something strange here. So this is, we call it G excess term. So this one, excess Gibbs energy, basically. Okay, so now, so this is the most general actual expression, and then we can look at the couple of the limiting cases, okay, special case. Now, so when this Gxs term, so basically Gxs is RT yeah. So, number one, when gamma A, gamma B, both of them equal to 1. So, we call this one as ideal solution. Do you remember that? So, when the activity is just changing linearly with the composition, so it means there's no interaction between A and B. That's what I say, yeah? And then activity coefficient equal to 1, and you call this one ideal solution. When it's the case, so Gxs equal to 0. Am I right? So then, Gibbs energy of solution equal to Xa Ga naught plus Xb Gb naught plus RT Xa So it's expressed this way. So ideal, just this one is the mechanical mixing and ideal mixing entropy term. It's almost like ideal gas solution. The formula is exactly the same as ideal gas solution when the total pressure equal to 1. So even in the liquid and the solid solution, because compared to the gas phase, solid and liquid is less, less actually the sensitive to the total pressure, because the pressure cannot change the volume of the solid liquid very well. So it's less dependent to the actual pressure. So when you have the pressure equal to 1, gas phase, the ideal gas actual solution Gibbs energy is same as the solid or liquid ideal solution of solid or liquid. Okay, the formula is exactly the same. And it means there's no interaction, so it means A and B doesn't actually produce some delta H of the mixing. No delta H of mixing. There's only delta S of mixing, yeah? Am I right? So, it's like this. It's exactly the same as the ideal gas solution. Number 2. When this G-axis parameter, and actually so, I'll just put in this one here. Let's put one more thing. So this one is eventually function of XA, XB, typically so this whole thing here is the summation, this is this function RT ln etc. And in general this value can be expressed by this kind of function of the composition, and this is function of the temperature here, and this is function of composition is multiplied here. Okay. And here Ij is the power of Xi, Xa and Xb. So multiplication of A power I, multiplication of B power J, and this Ij is just the index for corresponding actually power. Okay. So this could be basically, so omega AB power 1 XA XB plus omega power AB 1 2 XA 1 XB 2 plus like this. Okay, so this is just the value which is only function of temperature. Okay, so this 1 is just indexing for this power 1 and this 1 2 is the index for this power 1 to corresponding index, which is multiplied with actually the just showing actually what is actually the value which is multiplied with the certain actually mole fraction function here. Okay, so this is not real power. This is just index for these two. Okay, is it okay? So in general, G-axis parameter is expressed in this polynomial function. Okay, and when XA, XB equal to 1, this becomes 0. So that means all this value is 0. All this omega value is 0. Okay? I say W, but it's W in the Greek character, we call omega. So sometimes people actually typically using this one instead of this way, omega AB, Xij, this way. It's the same notation. Is it okay? You good? So I just want to say that G-axis parameter, which is function of your activity coefficient. Activity coefficient can be changed depending on the composition and temperature. So eventually this one can be expressed by any kind of polynomial function like this. And the only thing you have to remember is Ij, both of them should be power of Ij, both of them should be higher than 1. Because only one of these is 1 and one is 0. then it means when XA become 1, XB become, so for example, XA, and so this is power 1 and this is power 0, then when XA equal to 0, so this is 1 and this is still 1. So when pure B, this value will be actually affecting, which doesn't make sense. When it's pure B, you have only GB naught value should be, the same as the solution is same as pure B. I'm sorry. So anyway, so that's why IJ should be higher than 1. It's only affecting in the binary system, not in the pure A or pure B side. Okay? You don't get it? So when this is power xi, so let's assume you have this one. So this kind of the power. And if this is existing in this function, then it means when xa equal to 1, this is 1, this is power 0, so it's 1 automatically. This equal to 1, and then there's some value adding into the gxs parameter, yeah? So when xa equal to 1, so when xa equal to 1, if you look at this one, when xa equal to 1, so this term is ga, yeah? So solution Gibbs energy should be exactly same as GA naught, yeah, because it's pure A. But however, this is 0, but this term here, you'll have omega AB, 1, 0 term, which changing this value, yeah. So this is not anymore same as this one, because there's some additional term remaining in the excess parameter, yeah. So in order to prevent that, this one, this power, IJ, should be always higher than 1. Okay? That's what I mean. It's just mathematical expression. Okay? So when it's A, pure A, your solution Gibbs energy should be same as the pure A Gibbs energy. Solution Gibbs energy should be same as pure B Gibbs energy when it's the mole fraction of B equal to 1. Okay? Okay? Yeah. Yeah, omega and W is same basically. In Greek, we use the omega, and this is typical notation we are using in thermodynamic book, and some book we are using omega like this way. The same. Okay? It's capital, Greek character omega, small character omega in Greek. Am I right? So, omega. Not W, omega. It's corresponding to the W in the alphabet, yeah. Okay? Good? So anyway, when GXS, sometime, very, very special case, GXS term here is, when this value is changing very, very strangely, then GXS could be only omega AB power 1, 1, XA, XB. Okay, there's no additional term, only this term. Okay, so it means excess parameter is changing symmetrically depending on the composition of XA and XB. So when it is 0.5, you have maximum value or minimum value depending on this omega, the sign of omega. Okay, that case we call this one as regular solution. And when this is the case, this value is constant term. It's even not changing depending on the composition. Okay? It's constant term. Okay? Then this term is corresponding to the actual delta H of mixing. Because when you have the S of mixing, you need a temperature dependence here. Because Gibbs, we are talking about Gibbs energy. Gxs parameter would be Gxs of the enthalpy term, Gxs of entropy term. So Gxs will be, so Gxs should be A plus, for example, Bt term, and this is basically delta H of mixing, excess mixing, minus T delta S of excess mixing term because it's Gibbs energy. So when you say delta, or it's basically delta, Gxs is changed from the ideal actually the value. So this is on mixing term. So Gxs is delta H of mixing excess term minus T delta S of mixing of excess term. Okay. When this is regular solution, when this is constant, it means this one equal to 0 and this delta H mixing excess term is same as omega AB power 1 XA XB. So this is regular solution. So it's a special case. Okay? So ideal solution is very, very special case. And this is also another very, very special case. Okay? So ideal solution is one of subset of regular solution actually. When regular solution omega, this one is 0, then it become ideal solution. Okay? When A, B start to like each other, when there's actually some interaction. So theoretically, when I say ideal solution, there's no interaction. This is wrong. This is not actually correct expression. So the exact expression is like this. When you have A and A, there's always some interaction. Okay? When you have B and B, there's always some interaction. So let's assume AA have minus 1,000 joule interaction. Okay? BB have minus 2,000 joule interaction. When A and B together, AB, have the 1,500 interaction, then this is ideal solution. Because the AB have average interaction of AA and the BB. Okay? It's linearly changing. Okay? Then it's ideal solution. Okay? If the AB have a different from that ideal actually change, the interaction of AB is higher than that or lower than that, then you have ideal enthalpy of mixing. Because interaction is basically mixing. Is it okay? You good? That's what we call it regular solution. Theoretically also, there's no regular solution really happening. Why? Because when you start to have this omega AB is more negative than the original AB interaction. So AB have the more negative than original average of A and the B. Then you will have more tendency to make AB burn the inside of solution. AB connection will be more than average actually just a random mixing. So when you have this delta H of mixing become negative and negative, theoretically you can actually also change your ideal entropy term. Because the entropy cannot be ideal anymore. Am I right? Yeah? So, for example, if I have 50 student man or 50 boy and 50 girl or whatever, and if man and woman like each other, if man and woman, they don't know each other, they don't care, they don't want to actually have marriage or whatever, so they don't know actually this is man or this is woman. If you mixing, it will be just random distribution, yeah? It's ideal solution basically. Okay? They don't care who is actually next to me. So it's a random mixing. The chance to have A, B together can be calculated directly from the probability game or probability function, yeah? Am I right? So when you have chance to AA together, it's mole fraction of A times the mole fraction of A. When you have BB actually chance together, mole fraction of B times the mole fraction of B. And when AB is mole fraction of A, mole fraction of B plus mole fraction of B, mole fraction of A. 2 times of mole fraction of AB, yeah? That's a random distribution. But now, let's assume that AB like each other. Then AB want to actually sit together, yeah? So then the chance to have AB should be higher than the random distribution. So random distribution is ideal entropy. And because you have now interaction, theoretically, whenever you have interaction, your entropy cannot be random anymore. Do you agree? Theoretically. Yeah. So when AB have the positive interaction, then AB pair should be less than original random distribution. When AB have negative interaction, then AB pair should be higher than random distribution. Am I right? So, ideal entropy cannot actually cannot actually satisfy anymore when you have delta H is different than 0. Okay? But in order to make a very special case, and for the education purpose, let's assume that we still assume ideal entropy, and when this delta HO mixing, so omega AB, is not very far from the ideal case, then we still assume the entropy is reasonably ideal condition, and then only that additional enthalpy actual contribution by the interaction is going to this excess parameter. That's the regular solution model, regular solution. Is okay? You get it? The concept? And then, very general case, number 3, it's really function of xi, so omega. So number 3 is when you have this kind of case. This is not very general case, but sometimes people actually want to say this one. AB, 1, 1, mole fraction of A, mole fraction of B, plus omega AB, 1, 2, XA, XB, or omega AB, 2, 1, XA, XB square, and power 1, and 1 power 2. So this kind of case, you have one more term in this excess parameter. So when excess parameter is only omega AB, power 1, 1, and if this is independent of temperature, we call it this one as a regular solution. Okay? And people want to make always new name. So when you have now two terms, one is omega AB power 1, 1 term, and the other one is omega AB power 1, 2, or 2, 1. That's a small additional, one more additional actually term. They call this one as servo regular solution. It's regular, but one more down, servo-regular. So it means you can make a servo-regular if you like, yeah? And servo-regular, it's just, it's nothing special, but it just say, okay, I have the one more additional case. Okay? But in general, so number 4, general case. When it's general solution, so of course this GX parameter is really summation of any kind of combination. So when you go to the general solution, you can have excess enthalpy and excess entropy simultaneously. That's general condition. Okay? But when you go to this general condition, if you want to really do the mathematical calculation for your homework and for your midterm final, it's very difficult. So we almost don't go to that even subregular or general solution. Most of the time, we only go to this ideal condition and the regular condition in this lecture. Okay? Okay?
Can you get omega in the group or reference?
Yeah, omega. And omega is typically not given in the book. And actually what I'm doing is finding out omega. My research is really try to find out that omega depending on the activity data or some other data. Yeah. So finding omega is really one of the actually key knowledge for understanding the material chemistry. Yeah. This, you don't speak any English all the time. Yeah, so. Okay, in Korean. Yeah. So omega can be dependent on composition in this case here. Omega itself, as I mentioned, omega itself is only a function of temperature because the composition dependence is expressed here. This one, Gxs is composition dependent, temperature and composition dependent, Gxs parameter. And that actually split into two in this expression. One is temperature dependence term and the composition dependence term. Yeah. Yeah.
그러니까 그걸 만약에 이렇게 다이어그램을 그리면은 오메가가 이 선인 거예요. 여기 밑에가 XA, XB고 여기가 T면 오메가가 그냥 그 식이에요.
Yeah. So if you actually express XA, XB, but power, that is one case, but you have to draw all the different power, yeah? 1, 1, 1, 2, and etc. Yeah. Understand what I mean? So when you actually express this one, I'll show you, that one now. And when you express this one as a function of the mole fraction of B, so if it's symmetric term, then it's regular solution, more or less. And if it's asymmetric shape, then it's subregular or the general solution. Okay? Let's look at it more detail. Now in graph, then you will understand this one. So what I want to say is, okay, so we start with activity, and activity is necessary because we want to express this partial Gibbs energy of the component in solution. And once you know the partial Gibbs energy, then we can calculate any time what is the total Gibbs energy of solution. Okay? And there's this expression, and when you actually derive all this equation, eventually you're going to make this one as three different terms inside. And one is mechanical mixing term, so it's a linear change of Gibbs energy from pure A to the pure B. And then ideal entropy of mixing term, and then excess term. And this excess term could have the different, actually, this excess term can be expressed in general as a function of temperature and the composition. And when it is ideal solution, when omega equal to 1, ideal solution, so this one, when gamma, sorry, not omega, when gamma equal to 1, activity coefficient equal to 1, so in the ideal solution case, this excess parameter becomes 0. So solution Gibbs energy is same as the Gibbs energy for the gas solution at 1 atm. Okay? When this term is not 0, and one of the actually very important case is when this omega AB term is only existing, and that omega AB is constant term, then we call that one as a regular solution. And then when it's regular solution, this omega AB term is corresponding to this delta HO mixing, excess enthalpy of mixing term in the solution. Okay? Entropy mixing is still ideal entropy mixing. Okay? But if this one is not constant, A plus BT, then you could have also excess entropy of mixing as well. Yeah? That's specifically when you say regular solution, that is not regular solution. Some people say it's a regular solution, but by definition, it's not regular solution. When it's regular solution, you only have excess enthalpy of mixing, not excess entropy of mixing. Okay? And then if you want to make this one more complex, then we could have subregular solution, subregular solution, and etc. Okay? Good? Let me show you the expression, this expression in graph, then you're going to understand more. So let's assume this is mole fraction of B changing in this way. Same thing, mole fraction of B is changing this way. So this is G of solution. Okay? And this is delta G of solution. So when I say delta G of solution, it means G of solution minus XA GA pure, XB, GB, pure. So it's a mechanical mixing part that I call delta G of mixing, delta G of solution. So mixing of the Gibbs energy. Gibbs energy of mixing, basically. Sorry. So in this case, let's assume I have Gibbs energy of A, pure is here. A could be solid or liquid solution, solid or liquid, and Gibbs energy of B, liquid is here. Or Gibbs energy of A, Gibbs energy of B, solid or liquid, whatever. So it's same state. So solid, solid, liquid, liquid. Okay? And if there's no mixing term, if it's only mechanical mixing, it will be like this. So this corresponding to the GA naught XA plus GB naught XB. It's a mechanical mixing term. And then because of, even though there's no interaction, because of the ideal mixing term, we could have negative deviation like this. Okay? And then in this one, because this is now 0, this is now 0, and here we'll have negative deviation like this. Okay? So this is, let's assume, ideal. So when it's ideal case, how about my H of solution and delta H of solution? And how about my S of solution and delta S of solution? Okay? So H of solution. So I have, this sign could be different. This location could be inverse. Okay? It's really depending on system by system. But this is HA pure, and this is HB pure at the given temperature. Okay? Molar enthalpy of A, molar enthalpy of B. And this is like this. This is mechanical mixing and also ideal mixing. When it's ideal, there's no excess delta HO mixing. So this is ideal. Ideal case. Okay? So this is ideal case. Okay? And delta S of the solution. So now SA, let's assume this is SB. If it's mechanical mixing, it should be like this. But because of solution, you have ideal entropy term generating. So, like this. And this one is this amount. Okay? At 0.5, you have 0.5 R minus R 0.5 ln 0.5 plus 0.5 ln 0.5. So minus R ln 0.5 and R ln 2. R ln 2 at 0.5. Positive term. Okay? That's the ideal entropy. And when you actually express this one as a mixing, delta H. So when delta H of solution, it means H of solution is this one. Delta H of solution, it means H of solution minus XA, HA plus XB, HB. Yeah, minus of pure A and pure B. Okay, then this will start from 0, finishing at 0. Mechanical mixing or ideal mixing, same. It's all 0. Yeah? And delta S of solution is same. So we have S of solution minus XA, SA pure plus XB, SB pure. Yeah, that's delta S of mixing, delta S of solution. We are using same expression for Gibbs energy, enthalpy, and entropy. And in this case, so it starts from 0, 0. When it's mechanical mixing, there's no entropy change because there's no mixing entropy. But because of the ideal mixing term, we'll have this one. And this is delta S of ideal mixing ideal. Is it okay? So this is all ideal solution. So this is ideal solution. Okay, now when you have regular solution, so when regular solution, especially when regular solution omega AB is negative, then it means this one is not anymore like this. Omega AB is enthalpy of mixing. Enthalpy of mixing is negative term. So then, yeah, so this is omega AB, XA, XB. And this is symmetric, so here you'll have maximum at 0.5. Okay? So it's going down, omega AB, power 1, 1, power 1, 1. When omega AB, so this value, it means when omega AB is negative, less than 0, then you'll have this way. Yeah? When omega AB is positive, then you'll have the other way around. When it's positive, you'll have this way, yeah? Okay? Same thing. Okay? But when the regular solution, when it is regular solution, entropy of mixing is not changing. Entropy of solution is not changing depending on your omega value. So it's independent. So this will be same like this, or I mean it should be same curve, okay? It's not like different. Okay, it's independent. Same thing here, because omega is not contributing to the entropy term. It's only contributing to the enthalpy term, yeah? Is it okay? And now, if you look at actually now Gibbs energy. Gibbs energy is a combination of enthalpy and the entropy term. So here, when omega is negative, definitely this will be more negative. Okay. Okay, good. When omega AB is now positive, then interestingly, it's not going like this, because you have this ideal term here, so you cannot just suddenly going up like this. It should be. So I mean, it start with slightly like this, and then when you have more positive term, you go up like this. So omega AB 1, 1 is very positive. Omega AB 1, 1 is positive. And then of course, when your omega AB is very negative, this one will be more negative here. Okay? Same here. Okay? So this is general representation of the ideal solution and the regular solution in terms of Gibbs energy, enthalpy, entropy. Okay? But this is regular solution. But you can have subregular solution or general solution. Then what will happen is, so this one, it looks like regularly, or it have the minimum or maximum at 0.5. But you could have something like this, yeah? This is not regular. Okay? And same thing. Then we call it this one, subregular or general solution. Okay? You good? Same thing for the enthalpy. And entropy, when it's general solution, even entropy is not anymore ideal entropy. You could have excess entropy term too. You good? Okay? Because Gxs term equal to A plus Bt eventually, whatever. I mean, if it's only A plus Bt, then B term is not 0, then you could have excess entropy term there. Okay? In general, you could have temperature dependence term. Okay? Then this value is even changing. Is it okay? Good? Bad? Good? So this is the, we call it, general solution. Okay? The solid and liquid solution, sorry. So we run ideal gas solution. Gas is always ideal, except very, very low temperature and very, very high pressure. When gas actually start to feel the interaction between each other. That's what we call it real gas. And in that case, we have to use theoretically fugacity instead of the partial pressure in the inside of this partial pressure term, okay, fugacity, which considering the interaction between the gas species, okay. But most of the case, 99.9% case, we don't have to consider in that way. We can just assume that everything is ideal solution, okay. And then when you have the solid or liquid solution, ideal solution is very, very exceptional case. Most of the case we have some interaction. Why AB interaction should be average of AA or BB? Yeah? It's different atom. And they are each other, they are next to each other, they are close enough, so they should feel like some sort of the interaction, okay? And when you have the positive interaction between A, B, don't like each other, repulsive basically, then your activity coefficient, activity gamma A is higher than 1, and then the Gibbs energy here in general should be more positive. So it means less stable. It makes sense, yeah? Solution is less stable. Gibbs energy is less stable because it have repulsion force between A and B. So AB want to kick out each other, so want to go to the gas phase. So liquid or solid solution itself is not stable anymore. So in terms of Gibbs energy of solution, compared to the ideal condition, it's less stable. Okay? When AB like each other, you have negative interaction, then gamma A, activity coefficient is less than 1. Okay, so it like each other. In that condition, your omega AB should be negative term. Okay, negative interaction. Then your Gibbs energy itself is in general more negative than ideal case. So energetically, this is more stable solution than ideal solution. So it want to actually stay together. Okay, it good? One last thing I want to show you now. So we say that, okay, Gibbs energy of solution is the XA, GA plus XB, GB. And we call this one and this one as a partial Gibbs energy, yeah? Okay? Then, let's look at this graph. A and B and mole fraction of B. And when you have this Gibbs energy of solution, let's assume this is Gibbs energy of A and Gibbs energy of the B here. Okay? Mechanical mixing, I have my solution. Whatever is less or positive or less negative interaction, whatever it is, let's assume this is solution. Okay? At any given composition, at any given temperature. So this is at the given temperature. Okay? And let's assume that my solution have this composition. Okay? So I have solution of AB at composition of B equal to 0.6. 0.4 mole fraction of A, 0.6 mole fraction of B. What is my partial pressure? My partial Gibbs energy of A and B. From this graph, from this equation, and from this graph, this relation actually can be represented in here. So if I actually take that composition in this graph, if I draw the tangent line, this point and this point, this is partial Gibbs energy of A, partial Gibbs energy of B. So this is GA and this is GB. So that means when you have graph of solution, if you make a derivative at that composition of solution and the two end point of the XA axis, XB axis, that intersection point representing your partial Gibbs energy of A, partial Gibbs energy of B in the solution. Is it okay? It makes sense? It makes sense here, mathematically. This should be linear curve, and Gibbs energy of solution point, this one should be sum of this one, sum of this one. It's like kind of mechanical mixing of two partial Gibbs energy. Yeah? Now, this term, now let's look at this difference. GB equal to GB naught plus RT ln activity of B. Yeah? So this difference here will give you RT ln activity of B. Am I right? And this one, this difference, RT ln activity of A. Okay? So now from the graph, let's look at again activity and the Gibbs energy relationship. So if I know the activity of A and B for entire composition, then I know where this point should be with changing of this composition. Yeah? Then I can trace how this shape looks like. Okay? So activity and the Gibbs energy have one-to-one relationship. Okay? And also, okay, so if my actually Gibbs energy here is more negative like this, then if you actually draw the tangent line, the difference between this one become bigger and bigger, yeah? And this one, activity is less than 1, so it's always negative term, of course. This equal to this minus something, yeah? So activity is less than 1, so it's always negative. So when you have bigger and bigger difference, so when you have more negative Gibbs energy, when you draw the tangent line, you have more bigger difference, then activity become less and less smaller. So activity becomes smaller and smaller and smaller with a bigger difference. That makes sense here. So we say that when your activity is small, it means like each other, so solution Gibbs energy should be more lower. So you can see in the graph, when the Gibbs energy of solution is very low, your activity is very small. Make sense? So it's all related. Okay? And this is also a very important concept. In terms of graph, I'm just representing as a graph here, but when you have a solution, Gibbs energy curve into this kind of composition diagram, and whenever you know your composition, at that composition, if you draw the tangent line on your solution Gibbs energy, then two end point, two intersection point to the A side and the B side, that representing your partial Gibbs energy of A, partial Gibbs energy of B in the solution at that specific composition, at that specific temperature. Okay? And the difference between these 2 points giving you the RT ln activity. Is it okay? And for example, if your composition is different here, then you have different curve here. The activity is changing with the composition. Okay? So this is the old theory we need. And unfortunately, Wednesday we are not going to actually further expand this one for the exercise, but the week after, so next week, we're going to actually now see how we actually apply this kind of activity concept in the general actually thermodynamic calculation. Any question?